Okay, thanks everyone. So first of all, I'm Xianming. I'm from XPeng. So I'm leading the IT at the Autonomous Driving Center. So today probably I will talk about something different because I'm probably the only one from the massive production vehicle company. So first of all, let me introduce who we are. So we are XPeng. We build cars. We also build autonomous driving softwares. We build everything from end to end in our own stack. And most importantly, we are one of the AI-based companies, so we develop everything based on the AI models. So first of all, let me just try to show what we do. So first, all the videos is from all the massive production vehicles we directly shipped to consumers, not as something demos or not something experiment. Oh, sorry. In this video, we just show the safety functionality of the vehicle we shipped recently, last week, including weathers, fogs, waters, and also sometimes you see the small dogs, small debris in a very dark environment. And if you work on the home driver, you will see the debris, like the tires, is pretty annoying. It's pretty difficult to discover the obstacle in the dark environment and also trying to make a maneuver. Yeah, this is a spot arc in the very dark environment.
Only highlight is enabled.
All the vehicles we deliver doesn't have lidars. We don't have the cameras and radars. So all the stack you see here depends on the cameras. You see here, this is one of the challenges I like most. This is small debris. If you work for both companies, you will see this is a pretty challenging because it's very small, and you have to make a decision whether or not you want to yield. Okay, here you go. So here lists some of the capabilities we shipped to all of our customers' vehicles, including very competitive lane change. This is very common in China. If you drive in an urban area, dense urban area, you feel it's pretty challenging to make a lane change. You need to compete with the other agent to make a lane change successful. And this one, I don't want to show it. For this one, this is a navigation in the urban area, in the very narrow street, use a double point vehicles outside, and also there's a lot of VRDUs coming across. And the last one is very interesting. So, this one, the first one, even we don't have any navigation, we're just in campus we can still drive. This one, because all the stack is not placed, that means we don't have any television app, we don't have navigation and cameras. And so it enables us to drive through the constructions even though there's no road. You can see this is no road. There's no definition about road boundary or lakes, nothing. There are also some construction debris on the ground. The vehicle can still make the lane change or make the maneuver. Okay, here you go. So one is to try to recap what we experienced in the past decade for the autonomous driving software. So 10 years ago, everyone is busy with something of DAPA challenge, where you rely on a lot of lidars using the point cloud with the clusters in CPU and detect where's object or where's obstacles, and writing a lot of hard-coded heuristic SQL code to make the maneuver. So in this case, the entire stack is defined by a simple code. We call it software 1.0. So maybe 6 to 7 years ago, when detections or computer vision becomes more and more matured, people started replacing the perception and prediction using the machine learning models. But still, I think majority part of the stack is still C++ with certain part placed as well. And software 2.0 is very famous because it's proposed by Andy. That means if we want to iterate on software using data, you have to convert the entire software into AI models and try to do iteration based on the data centric. So from here, people say it's a AI models as a software. So currently we are at this stage where we build everything based on end-to-end AI models to drive the car. So for the next stage, we need to explore what we're going to in future. Based on scaling law, like everyone is going to expect scaling law. So some people say scaling law is that because we don't have enough data, but actually for AV companies or for the up-drive vehicle companies, we're not limited on data. We are not limited on the data, so it encourages us to think about how we can move forward in a massive scale, where we can collect data from the real world using hundreds of thousands of vehicles. We collect a lot of data every day, and then we train a very large vision models as a factory. So once you have this, you can distill the model into a smaller vehicles, smaller hardware on the vehicles. So we define this prototype as a software 3.0, but the name is so here the philosophy is once you can solve the problem using large scale foundation models, regardless of the prior data scales and 3D data scales, so we can always deploy the model onto the on-device environment. And then the problem becomes deployment problem, including protein quantification, distillation, and also building better on-device hardware. So this is the philosophy we are aiming for the next generation. So in order to build something like this, we create tools. Inner loop is we pre-train a foundation model using the scale data, and then do the reinforcement learning and SFT post-training to keep improving the model performance. And lastly, we do the distillation to squeeze the model into smaller ones and deploy the car. This is the inner loop, how we just iterate one circle. And that circle's outer loop. As I said, once we deploy model to the devices, we have hundreds of thousands of vehicles as a sampler in the real world, sample data, keep continuing training. So we define some outer loop where we continue training, or some people would say it's called online training. So we keep iterating like this until calculate the performance is good enough for L3 or L4. So I will talk a little more about why we need close training. Essentially reinforcement learning. So imitation learning can never achieve L3 or L4 because there's a lot of corner cases you see from Vivo graphics card. Like there's a lot of corner cases you can ever achieve by integer because you don't have the data, or you don't have discounted or warrant the equations or corner cases. So reinforcement learning can provide another solution where it can solve the corner cases. I will talk more later about this one. Here is how we train the model. We can divide the stages based on different perspectives. First one, you can divide it by pre-training alignment, which is a VR model pre-training, and then actual training. That means you build an actual net trying to train actually encoder, and then SFT, which is a supervised function to the instructor following, and then lastly, reinforcement learning. Or you can divide it based on the input and output models. The first model here is equals image and text pairs. So here we just train the correlation by doing images and languages or knowledge. The second part is we input the videos and actions. We want to model visual actions. It's just supervised learning. And lastly, during the reinforcement learning stages, inquiry is just video sequences and reward. We don't want to use actions as a creation to boost the performance of the model itself. So this is the second perspective design. And third perspective is actually we can divide in the middle. So here is the pre-training, and here is post-training. So this is how we define the stages. I will talk about stages. I will about how stages work. So this is a model architecture for foundation models, especially forward using VNG as a encoder. Interactive camera was dice cropped into the tokenizer and into the LNF at the going the actually generator, including visually CUT, and finally come to a stage of the reinforcement learning. And finally, we almost upload the 600 terabytes data daily into our cluster. So even though we are showing a very extensive result to show the schedule, but we still can see something from it. Once we increase the model size from 1 million to 3 million, 7 million to 72 billion, the ADE matrix keeps decreasing and almost showing some billion scale. And the other one is once we increase the data volume from 1 million to 10 million to 14 million to 40 million, we still see the metric decreases very sharply. So as long as for now, once we increase the model capacity and data scales, we haven't seen this one being separated. So this gave us the confidence to move forward with training an even larger model. Firstly, I will talk about environment or the data injection and goal injection. So in order to do this, we compose our data from like this. So in the last round of data, we are using 50 million video and text cards to train this stuff to inject knowledge into our VRI models. And the master version of our version right now, we consume 160 dB training data samples. So this shows some example of the data. The left one is TSL, the history of the vehicles who want to the model to answer a question like what is the status for vehicle, and on the right side, probably it is the traffic light. Now when we want to detect the traffic light status, one also want to ask a question like whether or not this traffic light control your lane. Once this step is doing, we also try to do the supervised learning SFT to enable the thinking for the COT. This is one of the very important steps because a lot of us use simulations. It's very complete. It's pretty straightforward. It's pretty hard to do it by say once you see the scene and with the overall actions. Sometimes you need more time in thinking. So that's why we enable train the COT. For the COT is a description of the environment, the reasoning, next steps, actions, and finally the trajectories. I don't want to go too much detail about this one, but we divided the training into 4 stages, including alignment, to give you the basic knowledge about what cycle is the training, COT, SFT, secret fine-tuning to enable the CFT. And we also introduced the reinforcement to do the COT, fine-tuning as well. And lastly, because we cannot run the COT or have the cars pretty heavy, we have to reduce the COT to avoid the CT where we reduce rotation. And that's the thing is, you can see from here is action-based here. Means we still need to output with the action will look like. The action is not some language of text output, it's described, it's visual token. We divide the actions into longitudinal action, the lateral action, including accelerate, decelerate, speed up, make left right turn, or change of stuff like this. So everything like this is derived from the trajectory look like from a vehicle. And lastly, I see something interesting from what we got from the COT and mind action. So here, each kind of is one called raging area or passage area, where the moving street traffic light is green and left turn traffic light is red. You have to move into the channel and wait in the waiting area. So the COT, after the COT training, you can see the hover trajectory can directly ask the car to go into the waiting area without too much other boost. And we can also control the COT output to make the vehicle to output different trajectories. For example, here, if we change the traffic light from right to green, the vehicle will move forward. So this is pretty important because we needed this COT and man action to generate something we can use once in the facility. And here it also shows some interesting results over on the meta actions. So in this man action, the default of the chooses the vehicle move straight as we are. And we can always change the man action to see how the vehicle moves. Here we can move we can change the man action that's speed up, changing lane to change the right lane, or stay in the lane. You can see your trajectory changes accordingly. And you can also ask the vehicle to slow down. The vehicle can reduce instead of the becoming denser. And here is changes the right lane without too much vehicle pressure, the vehicle can achieve the action to change the right way. And finally, this one is even more interesting. So once there's a lot of vehicles on right and you ask the vehicle to change lane to right, the vehicle stay in the lane. Compared to 20 vehicles on the right side, you cannot leave for change. So this is the first stage, alignment and COT. The second stage we do is the supervised finetuning. There's a lot of challenges in evaluation learning where evaluation learning only learns statistical mean of the all data we have. Sometimes we can learn about capabilities to run a vehicle by there's still some age also, for example, forward navigation and make a very comfort brake or something else. So we model this as we model the SRT as a kind of instruction following steps. So here is we curate the data, do the data curation to get a bunch of casting data we want to use in SRT stage. And we construct the key information prompt and formally we characterize as a instruction following. Here shows one example how the instruction following works. This is navigation. We ask the vehicle to follow the GPS, follow navigation to change lane into a maneuver or make a left feature and then make right turn. And then we use SFT to teach them all. You should follow this one. So this is a very straightforward instruction following task. And the solution is very straightforward as well. It's using SFT. Here shows an example as well. What do we do in the FSG stage? Including traffic light, intersection W, and navigation change called an NLC. For example, you want to make a lane change to the left lane, so you can make a left feature in that intersection. And here's a highway you call from of highway or get off the highway going to the ground. It's also instruction following. And the final way is from comfort rating. Comfort rating is not so straightforward, but it's still some kind of instruction following. You want a vehicle to stop comforting. We got very high brake, and you can give the bottom lot of examples what is defined as comfort and what to follow. And lastly, tap to the reinforced learning. This is very tricky. So before we go into reinforced learning is something you have to build a reward model or word model and do the reward action, do the reinforced learning. Yeah, everyone follow the same thing actually. Eventually for how driving is that the how to become safer. To do the reinforced learning, to drive safer, you probably just need 3 higher for reward. Safety offered. Second one, efficiency. You don't want to be stuck. And you don't want to drive slow on the 60 miles per hour lane. And also you want to follow the compliance of the traffic rule by traffic light, lane change, or the others. So the real value will be very straightforward to define. After applying these your functions, you enjoy feel about itself. Since we can achieve critical result, I'll show you down. This one is a user. On the left is something we didn't apply reinforced learning. You can see the vehicle trajectory calculated with the boundaries and is now very stable. On the right side, it's after reinforced learning. The vehicle knows how to decelerate and how to make sure the trajectories are smooth and don't collide with the low boundary. And this one is also on the left side after SFT. The model is very eager to move forward without keep the very safe distance with the VRU. And on the right side, the model can learn we should yield to the VRU on the safety distance and then move forward quickly. This is the similar issues. On the left side is something before the reinforcement learning where the model that's about how you yield to peel. And on the right side is after the reinforcement learning. Okay, so to conclude the summary, what we do is we try to explore the new pattern developing AI models for autonomous driving. So first of all, is the data-centric. The internal pipeline defined by the data. So schedule data through large foundation models to achieve a better performance continuously improving by daily iteration. So this is the first change. The second one is we wanted to change the model development cycles of patterns from pre-training to post-training to distribution to complete the whole cycle. And thirdly, keep doing this spontaneously online to receive the data and deploy the model to sample more data and capture the model itself. And lastly is how is software 3.0 probably after today, everyone should be remembered that the 3.0, which is to train a large model, distill or deploy the smaller ones on device and then forward. And some work we are going on, including deployment. We calculate everything based on the foundation model right now offline. And currently we are deploying this model to our commercial vehicles, consumer production vehicles. The second one we're working on is to keep making the alternative work contain a similarity. And thirdly is the learn model. Learn model is not only doing the 3D reconstructions, but it's more once you give symbol to the model, and the model should give you a word, and more about imagine rendering that. So hopefully next year I can just present you can work see. Finally, to conclude let me show some demos directly running the model over high to experience how it works. The first one, with the video quality is not too good. So minimum number lane change to avoid the dark parked vehicle on the road. Second one is a pretty dense urban area. There is a lot of traffic, so you can see our very first floor traffic. And some traffic is blocked in the middle of the way. You need to move the road to the right. And there's a lot of vehicles. Model didn't have any heart rate and no operations, no rules, no symbol like the C must go, just use the model inference. How you control it, go. And after that, you have to do road selections of the road. And this one is go through the construction area. I think there's some construction costs here. If you work on off-road or home driving, probably general addition of the construction costs is one of the big problem facing now. And the model right now here had pretty well. And lastly is we didn't have bread after training. Even there's a vehicles and there's some very use on all the junction. And you have to make a yield and move forward. In the third process, you can see from the curvature of the acceleration, there's no hard brake. So you will feel very comfortable with that. Okay, I think the summer is tough. Thanks everyone.